that done, I believe that most of us here speak several languages, some of them for talking to humans and some of them for talking to computers. Usually, these don't have too much in common, except for some of the words, maybe. Rivulet doesn't have any of these at all, but it does have pretty lines, just like calligraphy. How you make a programming language from that and how all that works, we're going to hear now from Daniel Temkin. One round of applause. Thank you.
Thanks. Yeah, so I'm Daniel, and I think I've had about 5 hours of sleep over the last 2 nights because my travel got all messed up, and I was flying over the Atlantic, and they sent us back, and then I had to go to Miami for some reason. So, if I go way off track, just like yell something out at me or something. But luckily, it's like bracingly cold up here, so it's going to keep me really alert. Anyway, I'm here to introduce the Rivulet programming language. And it's a language that's inspired by calligraphy and by mazes, mostly, but also by a certain kind of irrationality in natural language that I think is underrepresented in programming. And it feels really good to talk about an esolang at ZKM, because ZKM has been really supportive of my writing on esoteric programming in the past. I write a blog called Esoteric Codes. It didn't have updates for a few years, but it just came back because we just released the original source code for intercal that had been lost since the 70s. So we're really excited that we've been working with Don Woods and to get this public. So it's a good time to go back and see that if you have any interest in intercal. But the reason I had not been posting for a few years is because I've been working on a book for MIT Press. It's called 44 Esolangs. It is a book with 44 esolangs. It's the first artist monograph of esolangs, so it's really written avoiding most technical language. And I'm mentioning this because I really created the Rivulet language for this book. And the way the book is set up, it's actually a series of prompts for languages, some of which are implemented and some of which are sort of left for the reader to implement, or some which are sort of logically self-contradictory in some way that makes it impossible to implement, or so on. A lot of the prompts are very sort of open-ended. They are prompts. But Rivulet began as language 40, and it's a little bit more specific. It's a programming language written in tangles of lines. Commands are inscribed in the turns each line makes as it flows down the page. Strands never split. There are no alternate paths, and every command always runs. Should it leave the program in an undesirable state, another strand undoes its work. So that was my starting place for this language. And this is the first sort of complete program that I wrote for it. These are the strands. The strands are these lines. The strands meander through spaces, which are called glyphs. And the glyphs are demarcated with those sort of vertical dashes in the upper left and the bottom right. A glyph is a lexical unit. All the strands of a glyph always execute together. It can really only be understood in terms of the other strands in that same glyph. You see some of them start with 1, start a glyph marker, some have 2. Having 2 is sort of like indenting once. So the middle 4 are a block of code. In this case, it's a loop, as we'll see in a moment. So, the right way to really think of Rivulet is in the tradition of other 2D esoteric languages. Some familiar ones might be ASCII dots, which, it's a pictographic language that simulates circuits. At the bottom is bfunge, which is really one of the super old school languages from 1993, which, like ASCII dots, it has an instruction pointer, but instead of flowing along a circuit, it moves back and forth through the text of code. And then the language at the top is called Language of Lines, and it's by Lingdong Huang, and it's also pictographic, but it's something more idealized even than the idealized circuit of ASCII dots. They represent function calls in a low-level sort of combinator-like language. And it's the way that they split and the number of intersections that sort of denote computation in that. And the reason I'm showing that one is because it's the way that you follow Language of Lines is with our eyes, you can kind of think of it as moving through a maze, which is one of the things I was thinking about as I was designing Rivulet. Now, we can also think of Rivulet in the tradition of multi-coding languages. A multi-coding esolang is one where code has two different readings. One is code, and one is something else that is not code, such as an image or a series of photographs. The images here are, of course, for the Pete language. The photographs are for the light pattern language. And what's interesting about these is that we can just look at a Pete program as like an interesting piece of kind of pixel art. You don't have to know that it's also code, but how it functions as code impacts how it looks, and how it looks impacts the way that the code is constructed. And it's the relationship between those two things that makes it really sort of fun to make a multi-coding language. And that's sort of the same thought process that I wanted to have happen when you're writing code in Rivulet, even though Rivulet really does not have another reading apart from what it is, from what we see here. Like, you wouldn't look at this and say, oh, I'm just drawing a whole bunch of lines because I think they look cool. You can tell that something else is going on with it. So it's not truly multi-coding in the same way, if that makes sense. So mazes. Rivulet was obviously inspired in some ways by mazes. And one thing about a maze is it's very much like looking at a piece of code. There are mazes, of course, that we wander in without being able to see the whole maze, like a hedge maze, but that we experience from inside. But most mazes we see from above as a drawn maze, where we can see the entirety of the maze, and yet it doesn't, like, nothing is hidden from us, and yet the solution to it is not immediately obvious. We experience the same thing when we look at code. Just as we have to follow the paths of the maze with our eyes to make sense of it, we have to sort of run the program in our head to understand the behavior piece by piece in this sort of minute detail. The code to the right is a snippet from the infamous Terraria clone spaghetti code project. Now, there's two different types of mazes. There are the unicursal mazes and the multicursal. Unicursal are sometimes called labyrinths. And unicursal mazes have no splits. If you follow a unicursal maze, you always end up in the center or the exit, unless, of course, you stop or turn back. But the other thing about a unicursal maze is that if you complete it, you have gone the entire path. You've gone through every path in the maze. And I wanted to design Rivulet to be the same way. Every piece of code, every strand always runs. And so the way I approach that by making it turn complete is that sometimes we have rollbacks to some of that code, as we'll see. And I also looked quite a bit at calligraphy, especially the more blocky calligraphy that's done sometimes in Hebrew and in Arabic and in some constructed languages. The two images from the right are from the movie Prospect, which I just thought had a really cool language. And the piece to the left is a piece of calligraphy by Munir al-Sharani, who is a master calligrapher from Syria. And these are just some pieces that I sort of collected and looked at as I was working on the project. And then also, I was looking at space-filling algorithms. This is a piece that I made that resembles work by the painter Anni Albers, but it recreates it using a space-filling algorithm, which just sort of resembles her painting. She did these paintings that had these sort of different layers of these paths, so I did the same thing, but used this mathematical construct to mimic her work. And the thing that I liked about this is the compactness and the expressiveness of it. Those are the two things that I felt really make Rivulet what it is. The aesthetics and the feel of the language came first, and everything else comes second to that, which means that I can keep making up my own rules and make them more and more complex if I want, as long as they feel like Rivulet to me. So I will show more of the language in just a moment, but when I first put up the Rivulet language, there was a Hacker News thread, and so I got some initial feedback on it. And it was sort of interesting the way that people saw this. What does it make? How do people make sense of a language that has sort of more and more sort of complex rules? This was my favorite comment. Is this what it feels like to learn to program as an adult? I can brainfuck an APL with the best of them, and this is the most alien language specification I've ever read. But what I sort of did with this language is I decided that as long as it makes sense to me, it'll make sense to somebody else. And so I'll just keep going with it until other people start to pick it up. And that's what's happened. So let's get into some of the specifics of how Rivulet works. These are the first two glyphs of the program that I showed earlier, the sample program. And you can see, first of all, you can put them left to right or top to bottom. It doesn't really matter. And they have line numbers. And there's a few unusual things about the line numbers. First of all, that they reset at the beginning of each glyph, and also that they skip the number 4 for some reason. That's actually quite important because the way the line numbers work in Rivulet is they always start with the line 1, and then it's a series of successive primes. And that's the only way to read the code. Now, this is important because, well, first of all, I'll show you what our program does. I'm not going to keep you in suspense. It's a Fibonacci program that stops at number 21. And the way that we draw these is with box drawing characters, which are the pseudographic characters brought into Unicode that date back to like 70s text interfaces. And I'll go through this a little bit faster since I'm halfway through this already. Once we start using these box drawing characters in context, they become lexemes, which is basically they're given linguistic value. The only really important point of this slide is that the same box drawing character in a different context means something different. So if you have a corner, it can be a curve, it can actually be a corner in the flow of the line, or it could be a hook at the beginning of the strand, which gives it a special meaning. And in the same way, a half vertical line can be the glyph start or end marker, but it can also begin a certain type of strand. It can also be a ref marker that we'll see in a moment. So there's a whole bunch of aesthetic choices that people can make. They can make sharp corners if they want, they can make curved corners if they want, and so on. So here are two Hello World programs. These are both by Joe Wood. Joe Wood is a professor of visual analytics at City University of London. He's just someone who found the project and started writing code for it. Now, the top one is the sort of less Rivulet-looking version of the code, but it's the simpler one. And then the idea of Rivulet is that you're trying to compact the code as much as possible, so that's what we get at the bottom, is what it looks like when he does that. And then one of the things the interpreter does is it generates an SVG file of the code that color codes it to make it easier to read. So this is what this looks like. Now, the important thing I'm going to show here is that the strands are pointing. They have hooks at the beginning that point either to the left or up. That makes them value strands. And a value strand is basically referring to a constant. And the way you build that constant is by moving back and forth, left and right within the space. So these are the H's for his two versions of his code. It's the leftmost strands in both the programs. And the first one, it moves 1 unit to the right on line 7 and then 5 times on line 13. So it's just multiplying 7 by 1 and 13 by 5 and adding those together, and it gets to 72. And then he does the same thing with the other one, except he's moving to the left, so it subtracts 3 twice, and then he adds 13 6 times. So that's the way that the value strands work. And by default, these are all add assign. So we make a lot of use of what are called 0 strands, which are just value strands that have the value 0. These are all 0 strands. It's all read left to right. So the first one, it moves to the right once on 2, then once to the right on 5, and then back on 7. 5 plus 2 minus 7 is 0. All of these do the same thing. They're all doing nothing. Yes, so this is 3 different versions of the first glyph for the Fibonacci program. So again, for Fibonacci, we're going to stop at 21. And so what we want in the first glyph is to have a 0 and a 1, the first 2 values for the Fibonacci sequence, and then the number we're going to stop at, which is 21. So these are 3 different ways to get to that number. And they sort of make sense once you've seen this more. The first one moves to the right once on 2, and it moves back twice on 1. That's like a very common 0 strand. And the one next to it is 1 because it's adding 2 twice, and it's subtracting 1 3 times. So it's obviously easier when it's broken up into the segments, but you can still sort of learn to read it. So anyway, those are the value strands. That's the simplest type of strands. The next type of strand is referring to a list element. These are called ref strands. And the way that they work is they have a little gap at the end. So they also have hooks that point to the left or up. But whatever they point to, in terms of the start at the beginning of the other strands is the cell that they're referring to. So this is glyph 2 from the so actually, I think I'll just show. So one thing that makes this a little bit easier is to show you. Oh, so one of the other things that Joe Wood did is he made a little Rivulet editor so that as you're doing this, instead of typing stuff in like Sublime Text or whatever, you can do that, and then you can sort of select and drag your strand around to be able to sort of make it tighter or do whatever you want with it. But I want to show is. I should have, yeah. Okay, so this is just one of the examples of the second glyph that I was showing earlier. And this is what it looks like by itself. If you run the Rivulet interpreter with -p, it gives you pseudocode for what it's going to do. So in this case, it is adding 0 to the first element of list 2, that is adding 0 to the first element, to element 1, and then it's adding to element 2 from element 0. Because it's reaching around, you can see it's kind of reaching around, it's ending at the beginning, if that makes sense. All right. Let me go back here. Yes. Okay, 5 more minutes. So then what happens when you start working the ref strands is you can start chaining them like this, so that each one is copying from the one before, and you're able to copy values along. So this one, we're first assigning 16 to list 2 cell 0, then we're copying that to list 13 at the bottom, and then we're copying it all up to list 7, and we're copying from one element of 7 to the next, to the next, to the next. Okay, so let's say you want to do something besides add assign. Then you need something called an action strand. And of course, this works completely different than the 2 strands that we've seen so far. You draw them with hooks that point to the right or down. I color code them to match the strands that they're referring to. So the beginning of it has to be right below the beginning of the strand that it's referring to. And instead of how it moves left and right, it's how it moves up and down, creates a number, and then you have to look that number up at a table, and it tells you what this actually does. So in this case, this one is doing a replace. Instead of doing add assign, it's just doing an assign. Now, they can move towards the left or the right. They count up in either direction. If you move down, it's adds. If you move up, it subtracts. So hopefully that all seems simple enough so far. Because then there's other things you can do, like you can do actions across a list, or from either a single cell or from a list to another list. And then these all have their own markers as well, some of them by whether the action strand ends with a ref marker, which is the little gap, or whether it ends with a horizontal line instead of vertical. Then, of course, we have to be able to do the rollbacks, and that's done with question strands, which is 2 strands, one above the other, that don't have any hook, and they sort of meander through the space usually, and it's basically if it ends to the left or the right from where it began for the top element, and whether it ends on a horizontal or vertical for the bottom one, it rolls back the last block of code if what it's referring to, the list or the cell, is 0 or less. So those are the very basics. I know it's sort of a lot, but this totally makes sense. So the thing about this language is that it's really hard to explain, but once you start using it, it really makes sense. Everything really sort of fits together, and it's really pretty simple. These are 5 different versions of that Fibonacci program, and this is all using the SVG generator that I had. It generates in a whole bunch of different styles. But so these are a whole bunch of different ways of writing exactly the same code. And then finally, that editor that Joe Wood created, it uses a little bit of a different sort of color system. This is his version of the Fibonacci program as well. His does not stop at 21. It goes up to 377, which is what he gets by doing that big, huge loop and that big spiral in that first glyph at the beginning. So that's basically where this language is right now. It's still very new. There's only a few of us using it. I'm excited to see what other people might do. And again, here is the book that it's going to be part of, and my mailing list for it as well. I think there's only like a minute left. if anyone has like maybe one very fast question. Otherwise, we'll tie it up.
Yeah. It's a real pity. Not more time is left. But many thanks for that amazing talk.
Thank you.
One single question, whoever has one. Please, any question? Okay.
So besides the program being very pretty and interesting to experiment, especially in your mind, when you use a programming language, it starts invading your mind. Does it have like any practical application except the artistic aspect to it? Like, do you see it expanding more to it that it actually you can use it for real world applications?
Yeah, so it's an interesting question because I do get that question a lot for esoteric languages, and it's always tough to answer because the great thing about making an esolang, or really any programming language, is that like you create it with one thing in mind. It's like I had a certain style that I had in mind. I had a certain sort of like idea of how this would work and what it would look like. But then when other people use it, they're going to take it in their own direction. They're going to discover new things about it that I didn't know. And that's what's really exciting about making a programming language instead of just like some kind of like other kind of digital art, you know, is that it's community-based, it's collaborative, and people find their own way with it. So I'm really hoping that somebody finds some use for this that I hadn't anticipated, or creates stuff that looks really different than what I was thinking, or takes it in a really different direction. But that's yet to be seen.
Okay, time is up. Okay. Many thanks.
Thank you.
And everybody, please, as asked at the beginning, please take your beverages and trash with you. And whoever has not subscribed but be a volunteer, please reconsider, because this event couldn't happen without any helping hands. Many thanks. Have fun.